Hello everyone, welcome to the first video of section 1. In this section we are going to learn how to set up OpenGL ES in Eclipse, how to create an OpenGL ES environment, how to create your first shaders, and how to load and compile those shaders. In this video we are going to go through the installation of Eclipse and the Android SDK, as well as creating a suitable emulator for OpenGL ES programming. For this tutorial series, we will be using Eclipse for all of our coding, which is a free IDE that's easy to use. Eclipse can be downloaded from this website. The download links are on the right here for Windows, Mac and Linux. To install it on Windows, you download the file and run the executable and follow the steps on screen. For Mac, you download and unpack the tar file and place a resulting folder into your applications folder. And for Linux, you simply unpack the file and run the program. Although these are the links for the Eclipse 4.3, I will be using the 3.7.2, however everything should still work exactly the same. When you launch it for the first time, select a workspace and check the box to make this the default, and on the next screen click on the Go to the Workbench button, which looks like a folded arrow. After Eclipse has been installed, the next step is to install the Android SDK into Eclipse. First, from the Android developer website located here, click on Use an existing IDE and download the SDK tools for Windows. For other platforms, press the Download for Other Platforms link and choose the relevant platform for you for SDK tools only. After downloading the SDK tools, unzip them in an easy to find location, and then in Eclipse, go to Help, Install New Software, click Add, name it ADT Plugin, and add the following website. Press OK, and in the next dialog select Developer Tools and click Next, and continue till the end of the installation. After this, be sure to restart Eclipse, and when Eclipse restarts, in the Welcome to Android development window, select Use Existing SDKs, select the location you installed the tools and click on Next. Now we need to install the packages, so in Eclipse, go to Window, Android SDK Manager. This shows all the packages that you can add to your Android SDK. For the minimum configuration, you need to download the latest tools packages, the latest version of Android, and the Android support library located at the bottom here. However, I like to install everything so that I can develop on all versions of Android. After choosing your packages, click Install and the SDK Manager will install them into Eclipse. If there are any issues with installation, ensure that you're running Eclipse as an admin. Now that we have all packages installed, we need to set up the emulator. From Eclipse, go to Window and Android Virtual Device Manager, and then from here click New. Add a new device called OpenGL device. Select the Galaxy Nexus, as this is a good device to test OpenGL ES games. Set the target to 4.2.2, the CPU ABI to MIPS, and finally select Use Host GPU and click OK. The final step is to create a new project for the tutorials. So, in Eclipse, go to File, select New and Project, select Android Application Project and click Next. Name the application OpenGL Tutorials and change the package name to com.opengltutorials.breakout. Set the minimum to 2.3 as this is the minimum for OpenGL ES, and leave the rest as default and click Next. On the next screen, uncheck the box for Create Custom Launcher icon and press Next. Select Blank Activity, press Next again, and then name the activity OpenGL Activity and hit Finish. You now have Eclipse correctly set up with a suitable emulator for OpenGL ES. For these tutorials we will be using the emulator, but it is better to test on an actual device, so I recommend doing this if a device is available to you. In the next video we will create an OpenGL ES environment in the project we just created. Hello everyone, this video is called Creating an OpenGL ES Environment, and in this video we are going to create a simple OpenGL ES activity that will display a blue screen. First, we will just add a couple of lines to the OpenGL activity to initialize the surface view. First, add this code to the top of the class. Then, in the onCreate function, add this line. Don't forget the imports by highlighting the object with an arrow and clicking on Import. An easy way to do this, however, is to use a shortcut which is Ctrl-Shift-O. The next thing we need to do is perform a check to make sure the device we are using is compatible with OpenGL ES. These two lines in the onCreate function will get the information from the device so that we can check what version of Android is running. This code checks the information obtained previously to see what version of Android the device or emulator is using and returns a boolean based on this information. Next, we check if the device supports OpenGL ES using the boolean, and if it does, we set the renderer, else we make a toast pop up with a message saying the device does not support OpenGL. Next, we are going to add a couple of functions into our activity for pausing and resuming, which are important parts of the Android activity lifecycle. We implement these features so that when the user navigates out of or through the app, we can pause or stop certain features so that resources are not drained. For more information about the lifecycle, you can visit the Android developer website here. Back to the code. First, we add this line at the end of the onCreate function to set the surface view. Next, add a new function called onPause, which calls the GL surface view's onPause function, and create another function with the onResume with this code. For the final step, we are going to create the renderer that will draw all our OpenGL ES objects. First, create a new class by right-clicking on the project on New, go to Class, name the class OpenGL Tutorial Renderer, hit Finish. Next, in our new class, add these imports and make the class a subclass of renderer with this code. Create a new attribute for the context and create a constructor that takes this context and sets it. Next, we need to add 3 new functions necessary for the renderer. If you highlight the OpenGL Tutorial Renderer and click Add Unimplemented Methods, it will add the base codes for these functions. First, for the onSurfaceCreated function, located here, add this line that clears the color to blue. Then, in the onDrawFrame function, add this line that clears the color buffer for every frame. Finally, in the onSurfaceChanged function, add this line which sets the viewport when the surface is changed. Now, when we run the program, when we run on the emulator, we should see just a blue screen like this. We will use this renderer class as a base class for the rest of the series. In the next video, we will create our first basic vertex and fragment shader, which are used in the graphics pipeline and will be explained in further detail in the next video. Hello everyone, this video is called Creating Your First Shaders. In this lesson, we will start sorting our vertex data for our shaders, as well as creating a basic vertex and fragment shader. The first thing we are going to do is define our vertices for a simple square using an array of floats. With OpenGL ES, objects can be drawn with points, lines, or triangles, so for a square, the best way is to use 2 triangles. These vertices here will be used for our square in the OpenGL renderer class. The 0.5 value refers to half the screen width and height. Also note that the triangles are defined in a counterclockwise direction due to winding order. The next step is to sort this vertex data so that it can be read by OpenGL. For OpenGL to read our vertices, we need to convert the data from Dalvik environment to OpenGL's native environment by storing the data into a float buffer. The Dalvik environment is the virtual machine that runs apps on Android and is slightly different to OpenGL's native environment. To start with, let's add a new constant to our renderer for the number of bytes in a float and a float buffer for our vertex data. Next, we need to sort the buffer before we put the data in. Using this line, first we allocate the data based on the number of vertices times by the number of bytes in a float. We then order it in the correct order, and then we set it as a float buffer. Finally, we put the data into the float buffer. Next, we are going to create our vertex shader by writing them out as strings which are compiled internally in our program. In OpenGL, the vertex shader is used to transform the vertex data to its final position. Our vertex shader, however, will simply set the position of the vertex. Create a new string called vertex shader source and place the following code. First, the attribute vec4 apos is a vector made up of 4 numbers x, y, z, and w, which hold the position that is brought in from our float buffer. Next, in the main function, we set the position using apos. There are 3 types of variables that we can pass into the shader. Attributes, which are parameters that vary from vertex to vertex. Uniforms, that are used for values that are constant for each vertex or fragment. And varying, which are used to communicate between the vertex and fragment shader. Finally, we are going to create our fragment shader, which is sometimes called the pixel shader. The fragment shader is used to generate the final color of the fragment or pixel. So, create a new string called fragment shader source with the following code. The precision is used to set the precision of the floats in the shader, with median being the perfect balance between speed and quality. Next, the uniform vector is a vector that is set externally that is kept the same for all vertices unless we change it. In this case, it's used for the color of the fragment. Finally, in the main function, we set the color of the fragment to the uniform. We now have simple shaders that will draw our objects. In the next video, we will compile and link these shaders so that we can draw to the screen. Hello everyone, welcome to the final video of this section called Loading and Compiling the Shaders. In this video, we will take the shaders we created previously and compile and link them so that we can draw our square. First, let's add a new class that will be used to compile and link the shaders. Right click the folder, click on New and Class, and name it Shader Helper. Let's start by adding this static import. Next, we will add 2 short functions that will compile our shaders, one for the vertex shader and one for a fragment shader. Both will just call another function that actually compiles the shader. Now we will add our compile function to our shader helper class. Make it a private static int with 2 arguments, an int type and a string shader. The first part of this function will create a shader and then return 0 if it fails. Next, we will upload our shader source to our shader object before compiling this object. We will now check that our shader compiled properly, and if not, we will delete this shader and return 0. Finally, we will call the compile function for both shaders in the renderer class in the onSurfaceCreated function, as seen here. Next, we need to link the shaders before we can run the program, so let's add a new function to our shader helper called linkProgram, with 2 arguments, an int for the vertex shader and an int for a fragment shader. First, we will create the program and ensure that it works correctly. If it doesn't, we return 0. Next, we attach the 2 shaders to the program and then link the program. If everything is correct, we return the program, else we return 0. Finally, we add a new private int called program to our renderer. Then in the onSurfaceCreated function, we link the program and then use it. Our next step is to assign our uniform and attribute locations so that the correct data can be passed to our shaders. First, we will add 2 attributes for the color location. One string that is the name of our uniform in our fragment shader and an int that will hold the location. We will also add another 2 attributes, this time for the position. Next, we need to retrieve the locations from the shader. In the onSurfaceCreated function, at the end of the function, add these 2 lines that will get the location. Now that we have the locations, we need to supply it with data. Let's start with the position. After the previous code in onSurfaceCreated, write this code. This tells OpenGL where to find the data for the position from the start of our float buffer. The next line is a pointer to where OpenGL should find the data. The first part is the attribute location, then there's a data count per attribute, the next is the type of data, the stride, which is used for when there are multiple attributes, and finally where to read the data. Finally, we enable the attribute using this line of code. Our last step is to actually draw the square. Do this by adding these 2 lines to the onDrawFrame function. First, we will set the color in the shader using GLUniform4f and we will set it to red. Next, we will use GLDrawArrays to draw triangles, with the second argument setting it to the beginning of the array and the third reading the 6 vertices. Now, if we run the program, we can see that the square is drawn in the center of the screen. In the next section, we will look at the mathematics used in OpenGL, including projection matrices as well as vectors. Hello everyone, this section is called OpenGL Maths. and this is video 1 entitled OpenGL ES Matrix System. In this section we are going to create matrices and functions that will be essential in game development. In this video we are going to introduce matrices and vectors that will play a crucial part in our game as well as any future games you create. The first thing we are going to do is to create a matrix class. This class will contain 16 floats as a 2D array and will be vital for our game. So right click on the project, click on new and select class and name it matrix4f. The first thing we need to do is declare an array of floats. So this line will initialize the array. For now we will keep the class simple and have just one function that sets the matrix to an identity matrix. An identity matrix is a matrix that contains 1 on the main diagonal and 0 for the rest, as seen in this code here. This function will be used to reset the matrix. Our next step is to create a vector class. Vectors are also an important part of game development with many uses, such as lighting as well as to hold the positions and normals of objects. So create a new class called vector3f and add 3 floats for the x, y and z coordinates. Next we will add a constructor that will be used to set the values. This code will be used to set the x, y and z values whenever it's called. The final step for this video is to add 3 simple functions that will add 2 vectors, subtract 1 vector from another, and multiply a vector with a float. In Java, operators cannot be overloaded, so we will need to use functions instead. First, create a new function called add that takes a vector as an argument. Inside, add this code that will add 2 vectors together. Next, add another function called subtract that takes another vector again. Within it, place this code that will subtract 1 vector from the current one. Finally, add another function called mult that takes a float. Place this code that will multiply the vector by the float. We now have a foundation for our matrix and vector classes. During the rest of this section we will further build on these classes to perform more complex functions. In the next video we will be looking at vector math. Hello everyone, this video is titled Vector Math, and in this video we will be learning 2 vital functions for vectors, the dot product and the cross product. The dot product is a very important part of gaming with a variety of uses. It is used to calculate the cosine of the angle between 2 vectors and is used for the lighting equation, which we will cover later in further detail. To perform the dot product, first both vectors should be normalized as it makes the calculation simpler. Then, of the components are multiplied together before they are added to create one value. In other words, both x's are multiplied, then both y's, then both z's before adding the results together. This is the equation for the dot product. Before we calculate the dot product, we need to create a function that normalizes the vector. To normalize the vector, we need to find the length of the vector before dividing each value by the length. To find the length, square each value and add them together before performing the square root of the final value as seen here. Next we divide each x, y and z coordinate by the length to get the final value, using this. Now that we have our normalized vectors we can create the function that calculates the dot product. In the vector3f class create a new function called dot that returns a float and uses a vector3f as an argument. Next, calculate the x, y and z coordinates and then return the final value. Now that we have our dot product we can move on to the next calculation, cross product. The cross product is again a calculation between 2 vectors that results in a vector that is perpendicular to the other 2, which can be used as a surface normal. You can calculate each point of the vector using these equations, where a and b are the original vector and c is the cross product vector. After we have these 3 coordinates we return a vector containing the values. Now that we have the theory we can implement the function. So, in the vector3f class add a new function called cross that returns a vector3f and uses a vector3f as an argument. Next calculate the 3 coordinates using this code, and then create a new vector from these coordinates and return it. We now have functions that will normalize vectors, calculate the dot product and calculate the cross product. In the next lesson we will be creating a projection matrix and a view matrix. Hello everyone, this video is called Projection Matrix and Camera View, and in this lesson we'll be creating a perspective projection matrix as well as a camera class and a camera view matrix. There are a few steps that the vertex information takes to go from the data to displaying on screen, known as the graphics pipeline. First, the data goes through the vertex shader where they are placed into game space using the world view projection matrix. The data is then rasterized and sent to the fragment shader to draw the color before displaying on screen. We are now going to create the projection matrix and view matrix. There are two types of projection matrices that are used in games: the orthographic projection matrix and the perspective projection matrix. The orthographic projection matrix is used predominantly in 2D games, as objects on the screen will appear the same size no matter what their distance to the camera is. To create an orthographic projection matrix, we need 2 points: the left bottom near, known as the LBN, and the right top far, known as the RTF. With these 2 points, we can create this matrix that will be used to transform vertices to their correct space. The perspective projection matrix is slightly more complex, as a 3D point is in a frustum as opposed to a cube like the orthographic projection. For this matrix, we need 4 parameters: the field of view, which is the viewing angle from the top of the screen to the bottom; the aspect ratio, which controls the horizontal viewing angle relative to the vertical; the Z near, the inverted Z coordinate of the near clipping plane; and the Z far, the inverted Z coordinate of the far clipping. Using these 4 parameters, we can create this matrix. Now that we have the theory, we can begin creating the matrix. The first thing we need to do is create a new class called perspInfo with the following attributes for field of view, width, height, Z near, and Z far. Create a new constructor that takes 5 arguments for each attribute and set the attributes. Next, we need to create the matrix in our matrix4f class. First, make a function called persProjMatrix that takes in perspInfo for an argument. Before creating the matrix, we need to get these 3 attributes. First, the aspect ratio, obtained by dividing the width by the height. Next, the Z range, obtained by subtracting the Z near by the Z bar. And finally, we need the tan of half of the field of view. Now we have the valid attributes, we can create the matrix based on what we've seen already. This is done using this code here. Now that we have a projection matrix, we need to create a view matrix. To start with, we are going to create a camera class that will hold our attributes necessary for a view matrix. There are 3 attributes that are necessary for a view matrix: the camera position, the target for the camera, and the up vector. So with this in mind, we will give the camera 3 vectors, 1 for each attribute. Next, add a construct to the class with 3 arguments that will be used to set the attributes. When we create the view matrix, we need to multiply 2 matrices together for the camera, one that transforms it to its position, and a matrix based on the target, the up vector, and the right vector. So our final step is to add a function that creates a matrix from these 3 attributes. In the matrix4f class, add a new public void called camera transform. We only have 2 of the attributes at first, so we need to create the right vector using the cross product between the target vector and the up vector. Before we do this, we need to normalize the vectors, so use this code to create the right vector. Now that we have the right vector, we can create the matrix, so use these values to create the matrix. Now we have created 2 functions that will create a perspective projection matrix and a view matrix. In the next part, we will create functions that make a scale matrix and a translate matrix. Hello everyone, this lesson is called Transformation Matrix, Scale and Translate, and in this lesson we will be creating a scaling matrix and a translation matrix. But first we need to understand what a world matrix is. A world matrix is used to transform a 3D point to a world space. To create a world matrix, we need to create 3 matrices before multiplying them together: a scaling matrix, a translation matrix, and a rotation matrix. So the first thing we are going to do is create the scaling matrix. In our matrix4f class, create a new scaling function called scaleMatrix that takes a vector 3f as an argument. For a scaling matrix, the scaling values are placed in the main diagonal of the matrix, similar to an identity matrix. So, create the matrix with the following code. Our next step is to create a translation matrix, so create a new function called translateTransform with a vector 3f as an argument. For the transformation matrix in OpenGL, the translation values are placed in the 4th column. So with this in mind, let's create a matrix with the following code. We are now going to create a class that will handle all of our transformations as well as our camera and perspective projection matrix. So create a new class called Pipeline, and add these attributes for the scale, position, rotation, and then for the camera position, target, and up vector, for the perspective info, and a world transformation matrix and a world view projection matrix. Finally, now that we have our pipeline class, we're going to create functions that will set the attributes. First, add a constructor that will set the default scale, position, and rotation. Next, create functions that will set the scale, the world position, the rotation, the perspective projection information, and the camera. We now have functions that create matrices from a scaling vector and translate vector, as well as a pipeline class that controls all the world view projection information. In the next video, we will create a rotation matrix as well as the final world view projection matrix. Hello everyone, this video is titled Transformation Matrix, Rotation and Final, and in this video we will be creating our rotation matrix, as well as putting all three matrices together to create a world view projection matrix. In order to create a rotation matrix, we need to create three separate matrices, one for each axis. The three rotation matrices can be viewed here. As seen here, for each rotation, the row and column of the axis that the object is rotating around will always be the same as the identity. For example, in the X rotation as seen here, the row and column with the X-axis are all zeros except for this value here, which is 1. Before we create our rotation matrix, we need to create a new function that multiplies two matrices. To multiply a matrix, we need to multiply each row and column and add them all together for each number in the matrix. For example, for the first value of the new matrix, we take the first row of the first matrix and multiply the matching number of the first column of the second matrix, and then add all the values together. This can be seen more clearly in this code here. Now we can create our rotation matrix from the three rotations. In the matrix 4f class, create a new function called rotate transform that takes a vector 3f which consists of three angles, one for each axis. Next, we need to create three new matrices as well as three floats that turn the rotation values into radians. Now we create the three matrices using this code, and then multiply the three matrices together. Remember to multiply them in the correct order, Z, Y, and then X rotation, as they need to be in reverse order. If we do it in any other order, the results will be different and it will be incorrect. Now that we have the scaling matrix, the translation matrix, and the rotation matrix, we can create the world matrix. In the pipeline class, create a new function called getWorldTrans that returns a matrix 4f. Create three new matrices for the scale, rotation, and position, and then call the appropriate functions that will create the matrices from the vectors. Next, multiply the translate matrix and the rotation matrix, and then multiply that result by the scaling matrix before finally returning world matrix. Now we can finally create our world view projection matrix. Create a function in the pipeline class called getWVPTrans that returns a matrix 4f. First, call getWorldTrans to update the world matrix, then create three matrices for the camera position, camera transform, and perspective matrix and set them accordingly. Next, multiply the perspective matrix with the camera rotation matrix, and then the resulting matrix with the camera position matrix, and finally multiply that matrix with the world matrix, and return the final WVPTrans. We now have our world view projection matrix, so in a future lesson we will use this in our shader to transform our 3D points. In the next lesson we will learn about quaternions and their uses in games. Hello everyone, this video is entitled Theory Quaternions. In this video we are going to talk about the theory behind quaternions as well as implementing a quaternion class. Although we can perform rotations using Euler angles and matrices, this can produce one problem. It can cause the gimbal lock. This occurs when an object is rotated around one axis that causes another axis to lock up so that the object cannot be rotated around that axis. To combat this, we rotate the object with quaternions which consist of a rotation value and the axis to rotate around. It is also a lot more efficient to rotate with quaternions in a rotation matrix. We are going to implement this feature, however we will not need it for our game. So the first step to take is to create a quaternion class. Create a new class named quaternion with four floats named X, Y, Z, and W, as quaternions are made up of an axis and a rotation value. Next, create a constructor that takes in four floats and set them to the attributes. The next thing we need to do is to create a couple of functions that will be used to multiply quaternions, one with other quaternions and another with a vector. So create a new function called mult that returns a quaternion and uses 1 as an argument. Now create another function called mult with a vector 3f argument this time. This code will multiply 2 together and return a quaternion. Our next step is to create functions that are necessary for our rotate function in the vector 3f class. First, create a new function in the quaternion class called conjugate that inverts the matrix with this code. Next, create another function called normalize that normalizes the quaternion by dividing each value by the length as follows. Our final step is to create a rotation function in the vector 3f class that rotates the vector. Create a function called rotate with a float for the angle and a vector for the axis. The first step is to create the quaternion, and this is done by multiplying the axis by the sine of half of the angle and by using the cosine of half of the angle for the second part of the quaternion. Next, we conjugate the quaternion we just made and multiply this by the original quaternion and the vector to get the values for the rotated vector. Now we have completed a quaternion class which we can use for further games. Quaternions are a complex component which can be difficult to understand initially. For a further look into quaternions as well as more functions and uses, this is a great website. With this section completed, we now have fully functioning maths classes that will be vital for our game. In the next section, we are going to learn about the different types of lighting and how to implement them. Hello everyone, welcome to the first video of section 3 entitled Ambient Lighting. During this section, we are going to cover the 3 main types of lighting: ambient, diffuse and specular, as well as the 3 main lights used in games: directional lights, point lights and spotlights. In this video, we are going to begin with ambient lighting and begin creating our new shaders. To create a basic Phong lighting model, lighting is to be calculated at each point by adding the effects of ambient, diffuse and specular lighting. Each lighting term has its own equation, and these equations are added together to create the lighting model. This final equation is used by the vertex shader to calculate the shade of each vertex, and by the pixel shader to calculate the per pixel shading. The ambient term is the simplest lighting model, which consists of a colour and an intensity constant. This light affects the object uniformly, and it provides a constant light from all directions. The equation for this term is here, where IA is the intensity of the light and Ka is the amount of ambient light reflected from the object surface between 0 and 1. Our first step is to alter our shader helper class so that it is more suited to new shaders. Create a new function called build, which will create a new program using the 2 shaders. This function will use the code we had in the renderer to compile and link the shaders. The code for this is located here. Our next step is to create a new class which we will use as a base class for all our shader programs. So, create a new abstract class and call it shader program, and place the following attributes. These are our attributes and uniform constants for our shaders. Throughout these tutorials, we will be updating this class to contain more attributes for lighting, texture and particle shaders. Next, add this constructor that will call our new function. And finally, add another function to the class that makes it use the shader, which can be seen here. Our next step is to add a new function in the matrix 4f class that converts the matrix to a format that OpenGL can use. So create a new function called convertShader with this code. Now we can create a subclass from the previous class for our lighting. Create a new class called lighting program and make it extend shader program. Add the following attributes and uniform locations to the class. Next, add a constructor that calls the base class's constructor and then gets the locations from the shader using this code. Add another function called setUniform that sets the uniform locations. Finally, add another 2 functions that returns the A position location and the color location. The last step is to update the vertex shader located in the renderer class. So place the following code in the vertex shader. This puts the vertices into world space and the varying attributes are passed into the fragment shader. We now have an updated program ready for our lighting implementation. In the next video, we will learn about diffuse lighting as well as further updating our shaders. Hello everyone, this video is entitled Diffuse Lighting, and in this lesson we will be learning about diffuse lighting and further updating our shaders. Diffuse lighting represents light hitting the surface from a light source, and its intensity is view direction independent. The amount of light reflected depends on the angle at which the light ray hits the surface and the normal to the surface, which is seen here, where the yellow line is the light ray and the red line is the normal. Using the dot product of the light ray and the surface normal, the reflected ray can be calculated to show whether the light will be visible or not. If the angle between the light ray and the normal is greater than 90 degrees, or less than 0, the light will not have any effect on the polygon. The equation for this can be seen here, where IP is the light source's intensity, KD is the diffuse reflection coefficient between 0 and 1, and cos theta is the dot product. Our first step is to change our lighting shader program class to accommodate our diffuse lighting. For diffuse lighting we need to have the normal for each vector, so now we change our lighting shader program so that it takes normals to the shader. First go to the shader program class and add a new protected final string called aNormal, as seen here. Next, in the lighting shader program add a new private final int called aNormal location, and then in the constructor place this line of code to get the location. Finally, add a new function called getNormalAttribLocation that returns a normal location, as seen here. We now have to make a few changes to our renderer class to accommodate our new additions. So first, in the constructor, alter the vertices so they read as follows. This code adds normals and colors to the vertices. Next, add two private ints to the top of the class for the locations of the normal and the color, as well as an int for the stride. The stride, which is the number of floats between each vertex multiplied by the number of bytes in a float, will be using the GL vertex attrib pointer to get the correct values in the vertex data. Also create a private lighting program called lighting. Next, in the onSurfaceCreated function, initialize the shader program with the source code from the shaders and get the locations of the normal, color, and position. Finally, add this code that sets the attribute pointers and enables the free arrays for the positions, normals, and color. Now change the vertex shader so it is as follows. Now we pass the position, normal, and color into the vertex shader, as well as the world matrix, the world view projection matrix. We then pass the position, normal, and color into the fragment shader. Finally, add this code to the fragment shader. This code brings in the color, position, and the normal from the vertex shader and then colors the fragment using the color. If we run the program, we can see our colored square in the middle of the screen. We now have a further foundation for lighting. In the next video we will learn about specular lighting as well as further building on our classes. Hello everyone, in this video we will be learning about specular lighting as well as updating our code further. Specular reflection is shown when a light hits a shiny surface as some of the light is reflected to the viewpoint. The specular reflection depends on the incident angle between the light source and the surface, which is usually between 0 and 1. The equation for this can be seen here, where IP is the diffuse intensity, Ks is the specular reflection coefficient, R is the reflection direction, V is the viewpoint, and N is the material specular reflection exponent. For the reflection direction, that is calculated using this equation here, where L is the light direction and N is the normal. However, OpenGL has a function built in for this, so we do not need to calculate it. Now we are going to set up our shaders for the world matrix and world view projection matrix. First, in the renderer at the top of the class, create a new pipeline called P and then initialize it in the constructor. For now, since we like the square where it is, we won't set the transformation, rotation, or scale. We need to obtain a view matrix now, so at the top of the class, create a new instance of the camera, and in the constructor again, initialize it with the following values: position, target, and up vector. This will have the camera facing the Z direction. The final part of the matrix is the projection matrix, so create a new instance of perspinfo at the top of the class. Next, get the width and height of the screen using this code, and initialize the perspinfo with the following values. This will set the field of view to 45, set the width and the height, and set the near and far to 0.1 and 3000. Next, set the camera and perspective information in the pipeline using this code. Finally, in the onDrawFrame, set the uniform matrices using this line. Our final step is to update our shader to make it transform the vertices using our matrices. Place this code to make the shader transform the points to the correct space. If we run the program, we can see the square in the middle and the correct world space. We now have a shader that transforms our points to the correct world space. In the next lesson we will be implementing our first light, the directional light. Hello everyone, this lesson is called Directional Light, and in this lesson we will be implementing one of the simplest directional lights. Our first step is to create a base light that all our lights will stem from. So create a new abstract class called base light and give it these attributes for the color, the ambient intensity and the diffuse intensity. Next, add a constructor that sets the default values. Now that we have a base light class, we can start building light classes from it. A directional light is the easiest light to implement as it only consists of a directional vector with no origin point. It is useful for creating light across the whole scene or for simulating sunlight. So for the implementation, create a new class called directional light that is a subclass of base light. Give it one attribute, a vector 3f of direction, and a constructor that sets the direction to default. Now we need to create some strings to find shader locations, so add this code here to the shader program class. Our next step is to update the lighting shader program to add new uniforms and attributes to the shader. At the top of the class, add these attributes for the directional lighting. Next, in the constructor, set the attributes to find the locations in the shader as seen here. Finally, add a new function called setDirectionalLighting that sets the attributes for the shader using this code, as well as a function that sets the eye position. Now we need to add the code in the shader that will colour our pixel based on the light. First, create a struct called baseLight in the fragment shader with the same attributes as the class. A struct is a class that has all public variables. Next, we will create a struct called directional light with the following attributes. Next, add a uniform for the directional light so we can set the attributes using this code as well as the eye position and the specular values. Finally, we will calculate the light in the main function. First, create a function called calcLightInternal in the fragment shader that returns a vec4. Our first step is to calculate the ambient lighting created from the colour of the light and the ambient intensity. Next, we calculate the diffuse colour by first normalising the normal, then by doing the dot product between the normal and the light direction. We then set the default colour of the diffuse light to 0 and then calculate the light using this code. Finally, we calculate the specular lighting. Create the vector for specular colour starting with all zeros again, and then create a new vector for the eye direction. Next, create a vector for the light reflection, and then get the specular factor using these lines. Finally, if the specular factor is greater than 0, we calculate the specular colour. The last step is to return the total light. We then calculate the final colour by multiplying this value with the colour of the pixel, which can be seen here. To implement the light, we need to create an instance of the directional light. So in the renderer class, create a new directional light and set the attributes in the constructor as seen here. We then set the light to the program and then assign the camera position for the specular light. If we run the program now, you can see the square lit in the centre of the screen. We have now implemented the first light, the directional light, with ambient and diffuse lighting. In the next lesson, we'll be creating a point light. Hello everyone, this video is entitled Point Light, and in this lesson we'll be implementing the point light. A point light is different to a directional light as it casts light in all directions from the source. In games it is commonly used as a light on a wall or a candle lighting up a dark cave. It is also affected by attenuation, which is a drop in light intensity as the light gets further from the source. This is calculated with this equation. So create a new class called Point Light, which is a subclass of base light, and add these attributes. Next, add a constructor that sets the values to default as follows. Our next step is to add strings for new locations in the shader program, so add these strings. We now have to add the locations for each attribute of the point light. So in the lighting shader program class, add the following ints to the top. Now, in the constructor, get the attribute locations using this code. Finally, add a new function called setPointLight that takes in a point light and sets the uniform values as seen here. Now we need to implement the point light in the shader. In the fragment shader, create a new struct for a point light, seen here with these attributes, and add a new uniform for the point light as seen here. Next, add a new function called calcPointLight that takes in a point light and a normal. In the function, call the calcLightInternal function and then calculate the attenuation with the following code. Finally, return the colour times by the attenuation. In the main function, call the function we just created and add this value to the total light, as seen here. Our final step is to create an instance of the point light in the renderer. Add a new attribute for the point light, and then in the constructor create a new instance of the light with the following attributes. Finally, in the onDrawFrame function, set the light to the shader, and also move the setDirectionalLight into the onDrawFrame function. Now, if we run the program, we can see the square join in the middle with a point light. We have now implemented a point light in our game. In the next lesson, we'll be implementing the spotlight. Hello everyone, this video is entitled Spotlight, and in this video we will be implementing the spotlight. Our first step is to create a new class for the spotlight. A spotlight is similar to a point light, except that it only lights up a section based on the size of the cone angle, which can be used in games for a flashlight. To tell if the pixel is in the cone, we take the vector from the light origin, find the dot product between this and the light direction, and get the cosine of the angle. Next, we compare it to the cutoff value, and if it is larger, then we light the pixel. To create a new class called Spotlight that extends the point light class, and place the following code. The new attribute set the direction of the spotlight and the size of the angle, and the constructor sets the default. Our next step is to add strings to the shader program for the locations. So add these strings for the spotlight. Now we can create the locations and set the uniform variables. In the lighting program, add the following locations to the top of the class. Next, we get the attribute locations in the constructor just like the point light, as seen here. And then we create a new function called setSpotlight that sets a spotlight in the shader. We will now update our shaders to draw the spotlight. Create a new struct called Spotlight with the following attributes, and add a new uniform for the spotlight. Next, we'll create a new function called calcSpotlight that will calculate the light from a spotlight. To see if the pixel will be lit, first we find the dot product between the spotlight direction and the vector between the current pixel position and the light. We then check if this value is within the cutoff, and if it is, we calculate the light of the pixel based on the fall-off rate and with attenuation, else we return 0. Finally, in the main function, we will add the value of the specular light to the total light. Our final step is to create an instance of the spotlight in our renderer. Add a new spotlight to the top of the class, as seen here, and initialize and set the values in the constructor, as seen here. Finally, in the onDrawFrame function, set the light to the shader, as seen here. And now, if we run the program, we can see the spotlight lighting up part of the square. During this section, we have looked at 3 different types of lighting and have also implemented 3 different lights. In the next section, we will look at implementing textures. Hello everyone, welcome to the first video of section 4 titled Loading Textures. During this section, we are going to learn how to load textures into OpenGL ES, how to create shaders to draw the textures, and different methods of filtering, and their advantages and disadvantages. Up until now, we've been colouring our square using just colours, but there is another way of colouring our pixels. We can sample a texture. A texture can be passed into the shader and can be used to colour the pixel based on the UV of the vertex. A UV is another component of a vertex used to calculate which part of the texture to sample. UV is the axis for the texture, as XYZ is used for position in the world. Our first step is to create a new texture class that will load and bind the texture. Create a new class called texture with just one static function called loadTexture and make it return an int, as seen here. This method will return the ID of the OpenGL texture. First, we will create a new texture ID using OpenGL's glGenTextures function. After this, we will check if the ID is null and return 0 if it does to prevent any further errors. Next, we will take the image from the resources, place it into an OpenGL bitmap, and check if it is null using this code. Now we have a texture loaded, so our next step is to bind it to OpenGL. This line will bind our newly loaded texture to OpenGL. This will allow us to alter it and place it into the shader. Now we will set some default parameters for the texture to filter it. For now, we will just use the default values, but we will discuss the options in greater detail in a future video. Use this code to set the parameters. Next, we tell OpenGL to read the data and copy it into the texture object using this line of code. Now that we've finished with the texture, we can free up the memory by recycling the bitmap and then unbinding the texture using this code. Finally, we will return the finished int using this code. We now have a completed texture class that loads and binds a texture. In the next video, we will be creating new shaders that will colour our pixels using the texture. Hello everyone, this video is titled Creating New Shaders for Texturing, and in this lesson we will be learning how to create the necessary shaders to texture an object. We are going to make our texture shader program a subclass of the lighting shader program class. So first we need to add a couple of new strings for the attributes and uniform variables to our shader program. At the top of the class, add two new strings as seen here, one for the texture unit and one for the texture coordinate attribute. Our first step before we create the shaders is to create a texture shader program class that sets the constants and the uniform attributes. Create a new class called texture shader program and make it extend the lighting shader program as we want lighting to affect our textured objects. Add a new constructor that calls the constructor of the lighting shader program as seen here. Create two new private ints, one for the texture coordinate and one for the texture unit. Next we will retrieve the uniform locations like we did for the lighting shader program by using the following code. Now we will create a new setUniforms function that will set the matrices and texture as well as binding the texture to the unit, which can be seen in this code sample here. Finally, add a function that returns the texture coordinate location. Now that we can set the attributes and uniform locations, we can begin creating our shaders. We will use the previously created shaders as a base for our new shaders, so copy both of them to the texture shader program class. There are only a couple of changes to perform, so add a new attribute for the UVs called aTextChord, which is seen here, and create a variant attribute as well so we can pass the UV to the fragment shader. Remove the code that transfers the colour to the shader as we will be using the texture instead. Finally, add a new line to the main function that sets the variant attribute to the texture coordinate, as seen here. Next is our fragment shader. Add a new uniform sampler 2D for our texture called UTextUnit, as seen here. And also add a variant attribute for the texture coordinate, seen here. Remove the variant attribute for the colour. And then finally change the main function so that instead of vColor the light is multiplied by the colour of the texture. We now have our completed shader program class ready to draw our objects. In the next lesson we will be drawing the texture onto our square. Hello everyone, this video is called Drawing the Texture, and in this lesson we will be updating our vertex information to include the UVs and then draw our texture on the square. Before we draw our texture we need to add UVs to our existing vertices so that OpenGL knows where to map our texture. Go to the vertices in the renderer and change them so they read as follows. Since we are not using the colour in this lesson, we replace it with the texture coordinate. Now that we have our vertices set up, we can add a new attribute pointer for our texture coordinates. First, add a new attribute to the top of the class for the texture coordinate location with the following code. Change the lighting shader program to a texture shader program and initialize it in the onSurfaceCreated function. Finally, change the last attribute pointer from color to texture coordinate using this code. We also need to change the stride as well, as there are now 8 attributes rather than 10. Now we will add the texture to the renderer. Add a new int to the top of the class for the texture. In the onSurfaceCreated function, set the texture using our texture helper class and the texture we copied to the drawable folder. Our final step is to draw the texture using our shader. In the onDrawFrame function, use the shader program and set the uniforms, and finally draw the square. Now if we run the program we can see the square has been textured. In the next lesson we will talk about different methods of filtering the texture to obtain better results. Hello everyone, this lesson is called texture filtering, and in this lesson we will be discussing different methods that OpenGL can use to filter the texture to obtain smoother results. We have drawn the texture, but there are ways of improving the texture by filtering it. This is what is used to tell OpenGL what to do with the texture when expanding or shrinking it. We are going to learn about 4 basic ways of filtering a texture. Mip mapping. When a texture is generated, OpenGL can generate different levels and choose the most appropriate one based on the texture size. More memory is used, but rendering is faster. Bilinear filtering. This interpolates the 4 nearest texels to obtain the color of the pixel. For example, with a checkerboard pattern, after applying the bilinear filtering, it will appear black, white and grey rather than just white and black. This method is good for expanding but not very effective when shrinking the texture. Trilinear filtering. This is an extension of bilinear filtering, where OpenGL interpolates between the 2 closest mipmap levels and using 8 texels per fragment. And finally, there's nearest neighbor filtering. This is the method we use up until now, where the nearest texel is selected for each fragment, but this can result in a blocky look. We will be implementing mipmaps with trilinear filtering. We will now implement the mip mapping, which is done very easily. All we need to do is add a line to our texture class, as seen here. Finally, now that we've implemented mipmaps, we will add trilinear filtering, which again is relatively simple. Again, in the texture helper class, alter the GL text parameter lines so that they read as follows. Now if we run the program, although the square looks exactly the same, the filtering has been applied to it. We have now implemented texture filtering that has given us smoother textures as a result. In the next section we will be learning about particle systems and how to implement them. Hello everyone, welcome to the first video of section 5. During this section we are going to cover how to create customizable particle systems using shaders. Particle systems are objects in a game drawn as a set of points used to produce interesting effects. In games they are typically used for things like water, fire and explosions, which is what we're doing for our game. Before we create our particle shader program, we have to add a few string variables to the shader program class for the new uniform and attributes. So add this code to the top of the class. Our next step is to create a new particle shader program for our particle system attributes. Create a new class that is a subclass of shader program and add these locations for the shader. Next, add a constructor that gets the location of the attributes and uniforms from the shader with this code. Add a new function that sets a uniform attribute similar to the lighting and texture shader programs with the following code for the world matrix and the elapsed time. Finally, add some functions that get the attribute locations as seen here. Now that we have our new shader program, we can create our shaders. This shader will differ slightly from our other shaders as we will need more attributes to calculate the next position of the particle based on the elapsed time and the direction. So add the following uniform, attribute and variant fields to the vertex shader. Next, add the main function which will set the variant color, calculate the elapsed time and set the position. Now we will create our fragment shader, which is short and sweet. All it does is calculate the color of the fragment based on how much time has passed or the life of the particle. So, with this in mind, add the 2 variant fields from the vertex shader and this simple main function. We now have shaders ready for our particles. In the next lesson we will be adding a particle system to our main activity. Hello everyone, this video is titled Adding a Particle System, and in this lesson we will be adding a particle system to our main activity. Create a new class called particle system that will be used to add particles, find the data and draw on the system. First, add the following attributes to the top of the class for the particles, the maximum number of particles, the stride for the attribute pointers, the float buffer and the current particle count and the next particle. The array of particles holds the position, color and direction. Next, add a constructor that sets the particle array using the number of floats involved and also the float buffer. The next step is to add a new function that adds a particle to the array. The array of particles holds the position, color and direction of the particle as well as the start time before updating the float buffer with the new information. Add a new function called addParticle with 3 vectors for the position, the color and direction as well as the start time. Next, we calculate the offset for the next particle so that we don't override any of the previous information, and then we add a particle. Now we will set the particle using the offset, adding each attribute to the array using the following code. Finally, add this code that will update the float buffer with the new particle. Now we need to add a function that binds the particle data to the shader. Create a new function called bind with a particle shader program and set 4 attribute pointers, one for the position, color, direction, and start time. Add a draw function that simply draws an array of GL points. We will now create a particle emitter class that will be used to add particles to the particle system. Create a new class called particle emitter with 3 vectors for the position, direction, and color, and a constructor that sets these 3 vectors. For the final step, add a new function called addParticles that adds all the particles to a particle system. We now have a completed particle system class that will create, update, and draw a particle system. In the next video, we will add the particle system to the renderer to draw it. Hello everyone, this video is called Drawing the Particle System, and in this video we will be adding the particle system to the renderer and drawing it. Create a new class called Explosion with these attributes. This class will be used to create and draw our particle system. Add a new constructor that sets the position of the explosion. Create a new function called onCreate that will be used to set the particle shader program, particle system, and the start time for the particle system, as seen here. Next, set the particle emitter to a new particle shooter with the following position, direction, and color. Now that we have initialized our variables, we can draw the particles. Create a new function called render that calculates the current time, adds particles to the particle emitter before setting the particle shader program with the attributes, binding the data, and finally drawing the particle system. Our final step is to create an instance of the explosion in our render class. So add a new private explosion to the class. Initialize the explosion in the onCirfaceCreated function, as seen here. And then call its render function in the onDrawFrame function. Now if we run the program, we can see the particles. We now have a particle system drawn on the screen. In the next lesson, we will customize this particle system to look more like an explosion for our game. Hello everyone, this lesson is called Customizing the Particles, and in this lesson we'll be altering our current particle system to look more like an explosion. Our first change will be to alter the colours so that they vary between red, yellow and orange. Go to the particle emitter class and add a new array of vectors for the colours to the top of the class, as well as a random for the random colour. Another method of doing this is by lerping, which is a function that goes from one specified colour to another based on how much time has passed. Next, in the addParticles function, make the particle system randomly add different coloured particles using our preset colours. Also, in the constructor for the particle emitter, initialize the random colour, like so. Next, we'll make our particles spread out as opposed to a straight line. In the explosion class, add a new random, as seen here. Initialize it in the constructor, and in the render function set the direction to random floats for the x and z coordinates and keep the y as 1, as seen here. Now we need to alter the particle emitter class again. So remove the direction from the constructor and add it into the addParticle function instead, as seen here. Now that our explosion is more spread out, we need to make the particles fall back down. We can do this easily using the vertex shader by adding these 3 lines here. This makes gravity affect the particle based on how much time has elapsed. And now if we run the program, we can see a mini explosion. In this video, we have created a particle system that looks like a miniature explosion. In the next section, we are going to begin creating our Breakout game. Hello everyone, welcome to section 6 titled Breakouts, Assets and UI. During this section we are going to cover the main UI and assets of our game. In this first video we are going to begin with menu screens. Breakout is a classic game created by Atari in 1976 where the player must destroy all bricks using a ball and paddle. We're going to recreate this game for Android using the engine we've built up thus far. The first thing we need to do is place the assets into Eclipse. These are the assets I created earlier for the main menu. Drag and drop this file into Eclipse in all 4 drawable folders. Now that we have the assets in Eclipse, we can use them. Right click, go to New and select Other. Click on Android Activity and create a new blank activity and call it Main Menu on this screen. We now have our new main menu activity, so we will add our graphics to the background as well as the buttons to navigate. To do this, we will be editing the XML file which is used to create the UI. In the navigator, go to Res, then Layout, and open activity-main-menu.xml. What we see here is the graphical layout which shows how our final activity will look like. At the bottom here, click on the XML pane next to the graphical layout to look at the code for the layout. In here, the layout elements are defined along with their attributes. To add the background, we need to add a new attribute that loads the image from the folder we placed it in. This can be done by adding this line of code here. And now if we look at the graphical layout, we can see that our background is added. Next, we need to add the buttons that will be used to navigate to the game from the main menu. Go back to the XML file and add this code that will add a button that stretches across the screen. This code creates a new button, sets the size, and creates a new function that can be referenced in the code. For more information about XML files and what we can change, visit the Android developer website located here. Now that we have our main menu, we need to link it with the main game activity. Before we do that, we need to define the activity in the manifest file so that Android knows which activity is default. This time in the navigator, go to bin and then go to the Android manifest.xml. Click on the actual XML here. Remove these 4 lines from the OpenGL activity and add it to the main menu instead. Be careful with the editing, however, as if there are any errors it can stop the app from launching completely. Finally, we create the function that will activate at the start of the level. Go to the main menu activity file and in the onCreate function add this code that obtains the button from the XML and makes it change the level. An intent is used to bind between 2 activities and we use this to start the activity. We now have menus for our game that we can navigate to. In the next video we will be creating the user interface. Hello everyone, this video is titled Game Interface and in this video we will be creating the user interface for our game. Now that we have the main menu, the next thing we have to do is add the UI elements to our game. First we need to edit the XML file so that it shows the text views. Go to the res file, open the activity OpenGL file and add the code that can be seen here. This will add 2 text views as well as a layout for our renderer. Now we are going to add lives to our game. We want the user to have 3 lives, and if he exceeds this, we want the game to go to the game over screen. Create a new int called lives and set it to 3. Then add a function that returns the number of lives. To make it display on screen, we are going to use a text view that will show the player how many lives are available. In the OpenGL activity class, add a new text view and an OpenGL tutorial renderer, as seen here. Then change this part of the code so that rend is initialized and then the GL surface view sets this renderer. This block of code here is then added, which will first find the text view for the lives. And then here we use a runnable function that will ensure that the number of lives is updated regularly. Finally, we set the color of the text to white and then add the surface view. Next, we want to display the score to the user. So back in the OpenGL renderer class, add a new private int called score, set it to 0, and add a new function that returns the score. Next, in the OpenGL activity class again, add a new text view for the score, and then add these lines. First find the text view for the score, and then set the text of the score based on the score in the renderer. Finally, we need to add these elements to the display. Because we are rendering our game with OpenGL ES, we have to add our UI elements to the content view rather than just setting them. So instead, make the last part of the onCreate function read like. Now, if we run the program, we can see the score and the lives are shown at the top. We now have a nice, clear user interface for our game. In the next lesson, we will be creating the bricks for our game. Hello everyone, this video is called Creating the Bricks, and in this video we will be creating the bricks in our game that we will be destroying. In Breakout, the bricks are destroyed to give the player points. Our game is going to work in the same way, so that when the ball collides with a brick, it gets destroyed, the score increases, and an explosion occurs. Create a new class called Brick with the following attributes. We need a ball to check if the brick is dead, a vector 3f for the positions, an array of floats for the vertex data, as well as a float buffer for the vertices. We need to now initialize the variables for the brick in the constructor. In the constructor we will set the position, set the dead boolean, and initialize the vertex buffer. Next we need to add a draw function that will render our bricks. Add a new function called onDraw and add this code. This will draw the brick in its position if it is alive. We will also add a function that sets the attribute pointers using this code here. We need to add two more functions to this class, one that returns the dead ball and one that sets the position. First, add a new function called isDead which returns the ball, and then add a function called getPos that returns the position. Finally, we will draw the bricks on the screen. We will do this by using a for loop to set the positions of the bricks so that they are created in set columns and rows. First, create an array of bricks in the renderer class. In the onCreate function, add this code which creates a for loop and sets the position of each brick. Also, make sure you're using the texture shader program as seen here, and that you load the texture. Finally, in the onDraw function, add this code that will loop through all the bricks and render them. In the constructor, just before you create the new bricks, initialize the array of bricks, otherwise you'll have errors. Now if we run it in the emulator, you can see the bricks drawn at the top of the screen. We have now created our bricks for our game. In the next video we will be creating the ball and paddle. Hello everyone, this lesson is called Creating the Ball and Paddle, and in this video we will be creating two of the most important elements of the game. For the first part of this video we are going to create the ball. Create a new class called ball and add these attributes. We need a vector 3f for the position, one for the velocity, and a ball to start the movement. We also need an array of vertices for the actual ball and a float buffer. For the vertices we'll be introducing triangle fans. Triangle fans are similar to regular triangles except that the center vertex is defined first, and then triangles are drawn using that origin. Now that we have created the class we can begin creating functions. The first function is the constructor which we will use to initialize the variables. Add this code that sets the initial position, the direction of the ball, as well as initializing the float buffer. Next we will add an update function. We will use this function to update the ball over time based on whether the game has started. We also want the ball to bounce off the walls and ceilings, so this function will also check if we have reached the boundary and change the direction if it does. Finally, we need to add functions that get and set the variables. We need getters for the started ball, the position, and the velocity. So add these as seen here. We also need a function that sets the velocity, position, and the ball, so write this code here. Finally, we need a function that sets the attribute pointers for the buffer, so use this code. The last function we need for this class is a draw function. Using two triangle fans we can create a ball, so add this code here. Now, in the renderer class, add a ball and a lighting shader program to the top of the class. Initialize them both in the onSurface created, and then draw the ball using the color shading program in the onDrawFrame function underneath the brick as seen here. Now that we have our ball, we need the paddle. Create a new class called paddle, and add these attributes for the position, the vertices, the float buffer, as well as a static float for the limits of movement. We need to add a few more functions now to our class, similar to the previous one. Add a constructor that initializes all variables, as seen here. Next we will add the getter and setter. We only need one this time, both for the position, so add this code. Finally, add a setAttributePoints function that will set the locations for the buffer. The final step is to render the paddle. Add a function called draw that draws the paddle in a similar fashion to the bricks. Next, add an instance of the paddle to the renderer. Initialize it in the onSurfaceCreated function. And finally, draw it with the color shader as seen here. And now if we run the program, we'll be able to see the ball and the paddle. We now have our ball and paddle drawn correctly. In the next video, we'll be adding the sound effects and music to our game. Hello everyone, this video is entitled Sound Effects, and in this video we will be adding the sound effects and music into our game. Before we can start the sounds, we need to place the sounds into the project. Add a new folder in the res folder called raw and place your sounds in there. We will have sound effects for the explosion as well as a bounce sound for the ball. A good place to get sounds is from this website freesound.org. Now that we have sounds, we can begin building our sound manager class. This class will be used to hold all our sounds as well as playing our sounds and loop sounds. Add a new class called sound manager with these attributes. You need a sample, which is used to play our sounds, a hash map that is used to hold the sounds, and the audio manager is used to get the volume. Next we will add two functions to the sound manager, one that initializes the sound manager and one that adds sounds to the hash map. First, add the init sound function that initializes the sample, the hash map, and the audio manager. Next, add a function called add sound with just this line of code that places the sound into the sample. Next, we'll add a function that plays a sound effect. Add this code that retrieves the volume of the device, then plays the sound effect. Finally, we add a function that plays a looped sound effect. This code looks similar to the previous one, however this one loops the sound. We now have sounds implemented in our game. In the next section we will be covering gameplay for our game. Hello everyone, welcome to section 7 entitled Breakout Gameplay. During this section we are going to cover the main gameplay of our game. In the first video we are going to begin with the ball movement. Since we already have the code in place to move the ball, all we have to do is alter the boolean that we have already defined. At the minute the ball moves in a set direction until it hits a wall where its direction changes. In the constructor, change the started boolean's default to true. Now if we run the program we can see that the ball flies around the screen and bounces off the walls. Although the ball moves, there's a big problem in that the movement for the ball is not dependent on the frame rate, which can lead to lag issues. So to combat this we calculate the amount of time that has passed since the last frame and multiply the direction by the time. So first we will add two new floats to the top of the renderer class called elapsed time and current time. In the onSurfaceCreated function, set the current time to the current system nanotime. Then in the onDrawFrame function, calculate the elapsed time by taking the nanotime minus the current time, and then set the new current time. Now we need to change the update function so that it takes into account the elapsed time in the ball class. Edit the update function so it takes in the elapsed time and make the ball add the direction multiplied by this float. We also need to increase the velocity now, so set the velocity to 4050 as seen here. The final step is to set the update function in the renderer. Add this line of code to the onDrawFrame function just before you draw the ball, as seen here. If we run the program now, we can see the ball moves correctly, although it seems to lag as it's running on the emulator. In the next video, we will be controlling the paddle with the touch screen. Hello everyone, this video is entitled Paddle Input Touch, and in this video we will be changing the paddle's position with the touch. The first thing we need to do is set up a touch listener for our surface view so that Android listens to when the screen is touched. Go to the OpenGL activity class and add a new onTouch listener with this code here. This will call the renderer's onTouch function, which we are about to implement when the screen is touched. Now go to the renderer class and add a new function called onTouchEvent. This function will be used to find the position of the touch and set the paddle's X position to the finger. Add this code for the switch statement. This code gets the state of the motion event, which can be one of four. Action down, which is when the screen is pressed. Action move, when the finger on the screen moves. Action up, when the finger is removed. And action cancel, when the gesture is cancelled. We only need to concern ourselves with down and move. The code also makes the ball start moving when we touch the screen. Go to the ball class and in the constructor set the started boolean to false and add a new function called setStart that sets the started boolean. Next we add code that actually moves the paddle. In the switch statement where we left a space, place this code. This will change the touch's x coordinate to a value between 0 and 1, and then make that value into our bounds between -70 and 70, so that the paddle doesn't go off the screen. Paddle position is then set. Finally, make the width and the height a global variable for the class at the top of the class instead of defining it in the constructor as seen here. The final step is to set the onTouch listener to the surface view as seen here. If we run the program now, we can see that the paddle responds to touch movement. In the next video, we will look at controlling the paddle with the accelerometer. Hello everyone, this video is called Paddle Input Accelerometer, and in this lesson we will be learning about how to use accelerometer movement in our game. To access the accelerometer as well as other sensors such as the gyroscope or magnetometer on the device, we first need to get a sensor manager. This will hold all the sensors and can be used to retrieve values from all the sensors. First, where the OpenGL activity class is defined, implement a sensor event listener. At the top of the class, add two new variables, a sensor manager and an accelerometer. Next, initialize them in the onCreate function as seen here. Now we need to add some functions to make the sensor manager work. First, we are going to add a couple of lines to the onPause and onResume functions. When using the sensor manager, we need to disable the sensor listener when the device is put away, as it can drain the battery quickly. We also need to ensure we switch it back on when we resume, so add this code to the onResume function and add this code to the onPause function. Next, we need to implement two functions necessary for the sensor event listener, although we only need to concern ourselves with one. Add an empty function called onAccuracyChanged, as seen here, then add another function called onSensorChanged. This will be used to control our paddle with the accelerometer. We want to set the accelerometer value in the renderer when we obtain one, so place this code into the function. Before we add the code to the renderer, we need some new functions in our paddle class, as we want smooth movement when controlling the paddle. Add a new float called velx and initialize it to 0. Add a new function that sets this float. Next, add a function called update that is the same as the ball's update function we did before. This time, however, we calculate the paddle's next x value, and if it is within the boundaries, we set the new x position. Now we can update the renderer to update the paddle. Add a new function called setXLVals that sets the velocity of the paddle, as seen here. Next, in the onDrawFrame function, call the paddle's update function using the elapsed time. Finally, we want the ball to move with the paddle if the screen hasn't been touched, so add this code to the onDrawFrame function that does this. Although we can't test it on the emulator, if you run it on device you can see the ball moving smoothly with the accelerometer. In the next video we will be learning about broad-face collision detection. Hello everyone, this lesson is called Collisions Broad-Face, and in this lesson we will be learning about broad-face collision detection. One of the most important elements of this game, as well as many others, is collision detection. We need to calculate whether or not two or more objects have collided with each other so that we can progress the game. There are two phases of this, broad phase and narrow phase. Broad phase testing is used to calculate whether two objects can actually collide with each other. We calculate whether or not two objects can collide by using a grid to see if two potential colliding objects are within that grid. This can increase speed, as narrow phase collision testing can be expensive if there are many items. To calculate broad phase tests, we follow 4 steps. We update all objects, update the bounding boxes of each object, calculate what cell each object is in, and then check for collisions in the same cell. This is also known as a spatial hash grid. Our first step is to create a new base class that will be used to hold our objects. Create a new class called GameEntity and give it attributes for the position, width, height, and dead. Next, add a constructor that sets the attributes as well as getters for each one and a setter. Next, we need to alter our brick, paddle, and ball classes so they are subclasses of the GameEntity class. We also need to remove some of the variables located in each object, as they are now defined in GameEntity class. First, in the brick class, extend the GameEntity, remove the position and the dead boolean, and in the constructor, add a call to the super with the position and the width and the height. Also, remove the code that returns and sets the position. Next, in the ball class, do the same, but change the update function so that it says getPos instead. Finally, in the paddle class, update the constructor, remove the attribute and the functions, and also change the update function. Next, create a new class called spatial hash grid and add these attributes. We have a list of static cells where we place objects that don't move, such as the bricks. A list of dynamic cells where we hold entities that do move, such as the ball and paddle. The number of cells in each row, the number of cells in each column, the size of the cells, the ID, a list of found objects, and the width and the height offset, which we use to offset the grid. Next, we will add a constructor that will be used to initialize the grid, so add this code. This code sets the cell size, sets the cells per row and column using floatmath.ceil, which rounds a value up to the nearest whole number. The code also sets the dynamic and static cells as well as the found objects. Now that we have our spatial hash grid class, we need to add functions to make it work. First, add these two functions that insert static and dynamic entities into the cells. So do it with this code. This code calculates the ID of the cells that the entities are contained and places them in the corresponding cell. Next, we will add a remove function that removes an entity from the cells it's contained in. We do this when the brick is destroyed, so add this code here. Next, we need to add a function that clears the dynamic cell so that we can refill it every frame, so add this code. Now we move on to a more complicated function. This function, called getIDs, returns the IDs of the cells that an object is located in. An object can be located in a maximum of 4 cells if each point is in a different cell, so we need to check for overlaps between a single cell, 2 cells horizontally, 2 cells vertically, and 4 cells. Add this code that performs a check and returns the ID. As you can see from the code, the checks are performed as follows. For the single cell, by checking the bottom left and top right corners of the bounding box have the same coordinates. 2 cells horizontally, check by seeing if the bottom left corner is in one cell and the top right corner is in the cell to the right. For 2 cells vertically, the bottom left is in one cell and the top right is in the cell above. And finally, for 4 cells, each corner is in a different cell. This can be seen easily with this image. Finally, we add 2 functions that gets the possible colliders from the static and dynamic cells using this code. This code takes an entity and returns other entities located in the same cell or cells using the getIDs function we just created. Now that we have our completed spatial hash grid class, we can instantiate it in the renderer class. So add a new spatial hash grid and initialize it in the constructor with these values. Next, where the bricks are created, add each brick to the grid's static object list. Finally, in the onDrawFrame function, after the brick and paddle are updated, clear the dynamic list and add both of the entities. We now have a spatial hash grid that performs broad phase collision testing. In the next lesson, we'll be learning about narrow phase collisions. Hello everyone, this video is entitled Collisions Narrow Phase, and in this video we will be learning about narrow phase collision testing. Now that we have a grid with our objects, the next thing we need to do is perform narrow phase collision testing. This is performed by doing an overlap test based on the object's bounding box. For our game, we are going to use the object's height and width to make a bounding box around the position. We will then perform a rectangle collision test to see if the objects are colliding. In the renderer class, add a new function called isOverlap that takes in 2 game entities. This function will calculate the lower left value of both entities and then check for overlap using if statements to return a ball. Take a look at this code. The first check is to see if the left edge of the first box is to the left of the right edge of the second. The next check is to see if the right edge of the first is to the right of the left edge of the second. The final 2 checks are the same but for the top and bottom. This can be seen here easily, where the blue box is box number 1 and the black box is box number 2. Now we can check for collisions between our ball and our bricks. At the bottom of the update function, add this code. This code finds the ball's potential brick colliders, and if the ball is colliding with one, it changes position and sets the brick to dead. Finally, we perform a check for the ball and paddle collision using this code. This code checks for all dynamic objects, and if it collides with one of the ball, it rebounds. And now if we run the program, we can see that the ball collides with the bricks. In the next lesson, we will learn about how to implement scoring and lives. Hello everyone, this video is titled Scoring and Lives, and in this lesson we will be learning about how to implement scoring and lives into our game. For the score, we want it to increase when the player destroys a brick, so this can simply be done in the collision section. Add this simple line of code in the collision check that will increase the score. Next, we want an explosion to occur whenever the ball collides with the brick. Create a new list of explosions called explode. and initialize it in the constructor. Next, where the collision is checked, create a new explosion, call the onCreate function, and then add the explosion to the list. Finally, at the end of the onDrawFrame function, add this code that will loop through the list and draw the explosions. Once we complete the game, we want a screen to show up that congratulates us on the victory. Add a new activity called GameCompleteActivity, and in the XML file set the background to Breakout complete. In the class, add an onTouchListener. And in the touchEvent function, make the activity change to the main menu when pressed. Finally, in the renderer class, add this code to the onDrawFrame function that checks if all bricks are dead, and if they are, proceed to game exit. We have a scoring method in, but now we need to let the player lose the game using lives. In the update function, check if the ball's position is lower than the threshold, and if it is, reset the position, decrease the number of lives, and also check if the ball is going down, and if it is, reverse the velocity. Now we want to handle the game over screen once the player has run out of lives. Create a new activity and call it Game Over. In the Game Over XML file, set the background to Breakout Game Over. Back in the Game Over class, add another onTouchListener and make this activity return to the main menu again. Next, in the Game Over XML class, add this view, which we'll use to set the onTouchListener. And then, find the view and then set the onTouchListener in the onCreate function. Finally, add this code to the main game activity that changes the activity if the number of life reaches 0. And now if we run the app, we can see that the collisions work, the score increases, and the lives decrease. In this lesson we've implemented lives and scoring. In the next section we will look at adding the finishing touches to our game, including local high scores and monetization. Hello everyone, welcome to the first video of section 8, titled Creating a Local High Scores Table. In this section we will be adding the finishing touches to our game by adding high scores, in-app purchases, optimizing the game, and learning how to publish the game. We are now going to implement a local high scores table that saves scores on the phone. Create a new class called high score with these attributes. Shared preferences is used to save data to the device. For high scores we need scores and names. Next, add a constructor that obtains the shared preferences and then the scores from the preferences. Now we need to add functions to make the class work. First, add functions that get the score and the name. Next, we need a function that checks if the score is in the high score list. This code loops through the list of scores and returns true if the score is in the top 10. Next is the reset score function. This loops through all 10 scores and sets the score to 0 and names the default using the code here. Finally, this last function adds the score to the high score table. This function first checks the position of the score, then moves the other scores down a place before setting the new score in the correct position. Finally, the score is saved and then committed. Create a new activity called High Score Activity, and then open the activity High Score XML file. Add the background to the XML and these text views. Also add these two buttons for reset and back. Go back to the High Score Activity class now and add these text views for the score and names. These will be used to hold our scores. Also add the button and the reset. Next, set the text of the text view using the High Score class. And finally, add a button with an on-click listener that goes back to the main menu when pressed, and another button that resets the high scores. Now we need to update our game complete activity to show the score. Go to the XML file and add this text view that will be used to show if the score has reached the high score. Also add this view that we'll use to set the touch listener. Go to the renderer class now and add this code that will pass the score to the next class. And then in the game complete activity add these attributes, and then add this code that will retrieve the score and then set the touch listener on the view. Go back to the game complete XML file and add this edit text field that lets the user type their name. Go back to the activity and add this code that will display the edit text box if the score is a high score. The last step is to add the code to the onTouchListener that saves the high score to the table when the screen is tapped. We now have a completed high scores class that saves the high score on the device. In the next lesson we will learn how to publish our game. Hello everyone, this lesson is called How to Publish Your Game, and in this lesson we will learn how to publish our game on the Google Play Store. After finishing the product and creating a full release build, we are ready to show the world our game. Before we can publish our game, we first need to register as a Google Play Android developer on the Google Play website. Register your details and pay the $25 one-off fee to register as a Google Play developer. Next, we will begin creating the resources we will need for the uploading process. The first thing we will need are launcher icons that will be used on the device to launch our game. At the moment, the icon is set to default as the Android, so we need to create 4 new icons at different sizes for different devices. Here are 4 icons I have created previously and will use for the sake of this tutorial. Now we need to create screenshots of our game that users will see when purchasing our product. These screenshots will be the best parts of our game so that it will catch a person's eye and make them buy the product. I have created these screenshots previously and will use them as an example. If you have an Android device, you can plug it into Eclipse to capture screenshots. Before we upload the APK, you need to sign the app and compile the application for release. This can be seen on a website located here. Once the final APK has been created, we can upload the APK to the Google Play Store. Go to the Google Play Android Developer Console and press the Upload Application button to start the process. Google Play only allows a maximum of 50 megabytes for the APK, but if the file exceeds the limit, we can add expansion files. However, luckily for us, our file is under limit, so we will have no issue uploading the APK. Next, we need to complete the details of the APK. Add the description, promo text and the recent changes, and add the screenshots and the launcher icons to this part here. Finally, choose the application type and the category it falls under. Then we need to fill in the publishing options, which includes the content rating, which is everyone for this game, the pricing and the available countries. Finally, enter your contact information and accept the guidelines to upload. We can now publish our game on the Google Play Store. In the next video, we will be learning about different ways of optimizing our game. Hello everyone, this video is called Optimization Techniques, and in this video we will learn different ways of optimizing our game. There are many ways of optimizing code and improving the quality of code, so this video is going to go through a few ways of making our code look better. The first way of optimizing is by removing all unnecessary objects which can improve memory, so we are going to go through some of our classes and removing objects we don't use. A great feature of Eclipse is that it shows warnings for objects that are not used in the program, so we can use this to remove what is not needed. First, go to the renderer class and remove all unnecessary attributes at the top of the class. Another example can be seen in the particle emitter class. We can remove the random direction here. Another way of optimizing our game is by changing the constants in our game to static final constants. This means the class initializer method is not required, as the constants go into static field initializers in the dex file. The dex file is a compiled Android application code. In our game, there are 2 main constants we will want to change: the vertices and the shader source. First, change the vertices in the brick, in the paddle class, and in the ball class. Next, we'll change the shader source to static finals in the texture shader program, particle shader program, and finally in the renderer class, change the lighting shader program to be static final. Another way we can optimize our code is to remove calls to the getters and setters within the classes themselves, as it can be 3 times faster to just set the variable. We can also optimize code by making methods static when we don't need to access them, such as virtual methods. One of the most important things you should do when coding is remembering to comment your code. This is vital for you to understand what exactly is going on, and it makes it easier for other people to understand as well. So add comments to your code whenever possible. Let your code be easy to understand and be clear with your comments. Take a look at the code included with these tutorials for examples of how to comment correctly. We have now optimized our game. In the final video, we will learn how to add in-app purchases to our game. Hello everyone, this video is titled How to Add In-App Purchases, and in this video we will learn how to implement in-app purchases. Before we begin adding in-app purchases, we first need to set up a Google Wallet merchant account that will allow us to sell products. Go to the Google Play Developer Console, click on Financial Reports, and then press Set up a merchant account and fill in the details. The next step is to add the in-app billing service files to the source folder. This allows you to activate in-app purchases. To get these files, normally you download the Google billing library from the SDK manager located here. You then navigate to the folder to obtain them. However, for the ease of use for the tutorials, the files can be located in the billing folder. Click and drag it into Source, Com, and then Android. We also need to add the helper classes to the project, which were created by the Android development team to make the implementation a lot simpler. These are located in the folder with the in-app billing service file. You can also find the files wherever you installed the SDK. We will also need our license key to use in-app billing. Go back to the developer console, go to the APK, and click on Services and APIs. Copy the license key seen here over and save it as a private static string in the main menu. In your final game, it's best if you use multiple strings and add them together, or hide it on your server so it's not easily found. Next, we need to update the manifest file so that we can use billing within our app. We need to add a billing service and receiver, as well as actions and a permission. First, add the service and receiver as well as the intent filter shown here. Next, add this user's position just below the application line. Now we can begin implementing our in-app purchases. For this example, we want to give the user the option at the start to buy 3 more lives for their next game. We need to have an SKU so that Google Play returns the correct item at the correct price. For now, we are going to use the test SKU, Android test purchased, so add this string to the top of the class. For a real SKU, we need to set it up on the Google Play developer console. Add 2 implements to the main menu class, on IAB setup finish listener and on IAB purchase finish listener. These 2 listeners will be used to deal with the in-app billing when the setup is complete and when a purchase is made. Add the necessary functions for the listeners. In the on IAB setup finished function, we will activate the button if the in-app billing works using this code. We will also query the database for any existing purchases, and if there are any, we consume the purchase using this code. Also add these attributes for the in-app purchase helper, as well as the life offset. The last function we need is the on IAB purchase finished function, which checks if the purchase was successful, and if the SKU is a match, it consumes the purchase, increases the lives. Finally, add this button to the XML file that we will use to test the purchase. Set the onClick function in the menu activity class to this code. Now that we have our purchases working, we want to send our lives to the main game. Place the life into an extras bundle like we did with the score in the high scores video, and pass it through to the renderer class when the user hits start activity. Finally, we need to extract the data from the bundle and add the extra lives to the total. In the constructor of the OpenGL activity class, retrieve the value of the lives and set them to a new function in the renderer called setExtraLives. Next, in the renderer class, add the new function we created and add together the total. We now have in-app purchases implemented in our game, but they can only be tested on the devices emulators do not support it. Thank you for watching these tutorials. I hope you have learnt a lot, and I look forward to seeing your awesome games on the store.